Today we're talking about the rate law. What's the rate law, you ask? Well, I'm glad you asked. Let's talk about it. Here's what we know so far about chemical reactions and the rates of those chemical reactions. We know that the reactions happen. And I can't believe that some of you are writing that down. We also know that there are ways to manipulate the rates. We can change concentrations, we can heat it up, we can cool it down, we can maybe add a catalyst, and there's a lot of things that we can do. There's also ways to determine the rate. We have something to measure, and then we have to keep track of time. But what is the rate law? Well, the rate law is then this. Now, we don't need the definition, so you don't need to write it down, but I do want you to understand what that thing is saying. I know that changing the temperature changes the rate, but by how much? I know that changing the concentration of a reactant will change the rate, but by how much? And the rate law turns those ideas into this mathematical expression. And it's always in terms and only in terms of the reactants, because a reaction is reactants making products. So doing anything with the products really won't affect how fast the reactants are doing their thing. Now, there is some bad news. Sorry. And the bad news, though, is that I cannot look at a reaction equation and say, this is the rate law. I cannot theoretically come up with the rate law. I need to have experimental data. Now, the good news is, I'll be giving you a lot of that data. It's not something you have to come up with on your own. However, we do have to have numbers to work with. We can't just work with a chemical equation. Now, what does a rate law look like? We'll deal with what a rate law looks like before we deal with what the data looks like. The rate law is going to be for a reaction, and it's going to be for a reaction at a given temperature. You'll often in the question be told the temperature, but you'll rarely have to use that temperature number. It's just that changing the temperature will change the rate. The rate law is going to be related to the production of products, or I guess consumption of reactants. But if I were to look at that, now that line, what we have there, should look kind of familiar. I know the rate with respect to one thing in moles per liter per second. The rate law is going to express that rate, that number that could go in blank, in terms of K times the concentration of A to some exponent, concentration of B to some exponent. And it's important to understand that K is going to be a rate law constant, although it's one of those constants that can change. Change the temperature, change the rate. If I had a catalyst, if I change some other conditions other than concentrations, the value of K will be changing. However, for our purposes, every time we do this reaction or that reaction, the K that goes with it and stays with it, and will be a constant at those conditions. And of course, we know that the square brackets mean concentration, and the exponents are not balancing coefficients. Well, how do we get the exponents? That's where we come back to the experimental data. However, we need to have some background math. We need to remind ourselves how exponents work and what they do, because what we're after is essentially this. Now, you don't need to write this down, but I do want you to follow the math very carefully. We have x to some exponent, and yeah, I'm using m again, and that's going to equal some answer. Now, what's important is not that I know how to do exponents, but I know how to follow through. So do pay attention to that one part. I'm going to fill in this table. Now, what I'm going to do is I'm going to start out with value of x of 1, value of m of 0. So 1 to the exponent 0, oh, that's easy, that's 1. Anything to the exponent 0 is 1. What's more important, though, is what happens when I make x equal to 2. So I've doubled x. Now, x to the exponent 0, well, 2 to the exponent 0 is also 1, which means I've had no change on my answer. Now, take a moment, think about where I'm going with this. X is going to become my concentration. So going from the first line to the second line, I've doubled the concentration. Both of them are to the exponent of 0. I've had no change in the answer, although my answer is eventually going to be the rate. So if I change the concentration and I don't change the rate, that must have meant the exponent was 0. Or if I change the concentration and my exponent is 0, I don't change the rate. That comes back to us later. Now, what if I have an exponent of 1? Well, I'll start out with a baseline. 1 to the exponent of 1 is 1. Now, if I double it, and again, I'm thinking of this and through in terms of eventually doubling my concentration. If I double it, 2 to the exponent 1 is 2. So I double 1, I double my answer. I double the concentration, and I double the rate if my exponent is 1. If I tripled that thing, tripled the concentration, I will have my rate go up by a factor of 3 as well. Triple the concentration, triple the rate. My answer goes up by the same amount as the other because the exponent is 1. All right, what if I made the exponent 2? And we won't do much more than fill this in. But if I start out with my baseline, start out with a concentration, or I start out with a number, raise the exponent 2, and I get an answer. 1 to the exponent 2 is 1. What if I double the number? If I double a number, raise the exponent 2, my answer changes by a factor of, 4. Again, think in terms of concentration. If I double the concentration, that's my x, my answer, my rate, goes up by a factor of 4 if the exponent is 2. Well, what if I were to triple it? If I triple my value of x, my answer goes up by a factor of 9, 3 squared. All right, so that math is really simple. We've been doing exponents for a long time, grade 9 at least, probably earlier. Well, let's do exactly the same thing in science, in chemistry for reaction rates. So we need a reaction. We're going to use this one. Now, the products, there's actually 3 products on that one. I was going to fill it in, but I ran out of room, so I'm not going to worry about it too much. What's important is the reactants. The products actually don't, the products are important, but they don't affect the rate at all. Now, I actually encourage you to write this down so that you can follow it through and see where the numbers go and what we do with them, right? So I guess you could go back and keep flipping back to this chart, but it'd be a whole lot simpler if you had it. Okay, I want to look at this chart and how we use it because that's important as well. We start out with a baseline. Now, it really doesn't matter what the baseline is. We could pick any one of those trials as a baseline, but 1 is usually the one that we use. And then, as we compare 1 with 2, for example, we see that one of the concentrations has increased and the other one hasn't. And that's really important. It doesn't matter if we double it, as we did in this case, or we triple it, but what's important is that one thing changes and the other thing or things stay the same. So if I've got 3 reactants, change 1 at a time. If I have 2 reactants, as in this case, change 1, hold the other one constant. And you'll notice that the rate changes. And then if I compare the other one, I find out that only one thing changed. So I've changed the concentration of the other reactant and kept the first one constant. It doesn't matter if it's 1, 2, then 1, 3, or if it's 1, 2, then 2, 3, or something like that. It doesn't really matter what it is. I'm looking for combinations where only one thing changed. What if 2 things change? It's possible. It's more work, so we'll try to avoid it. It doesn't matter if it goes up by a factor of 2 or by a factor of 3 or whatever. We want to know what that concentration did and then look at the rate. All right, so how do we do that with the rate law? And how do we bring in all that other background math that we had? Here we go. Rate law is going to have that basic form. Now I want you to keep an eye on the exponents because as we figure them out, we're going to fill them in. So we start out comparing round 1 with round 2, or trial 1 with trial 2. And we find out that in trial 1 compared to 2, I've doubled the concentration of the bromate, BrO3 ion, doubled that, and kept the other one the same. So NC in this case is no change. And what happened to the rate? Well, the rate changed by, well, take the rate of the bigger one divided by the rate of the smaller one, and I have it went up by a factor of 4. That's not the important part. The important part, remember I'm looking for an exponent, is that it's 2 to the exponent 2. Remember before when I doubled the rate and my answer went up by a factor, I doubled my x and the y went up by a factor of 2 squared, that kind of thing? I'm looking for the exponent on 2 that will give me 4. Once I know that exponent, I can fill it in. So my rate law just changed. Now I'm looking at the other one, the trial 1 versus trial 3. There was no change in bromate, but there was a change in the bisulfite, HSO3, 1 minus charge. It doubled. What happened to the rate? Well, the rate went from the new one on top, the baseline on the bottom, and that comes out to 2. That's not as important as 2 to what exponent? Well, 2 to the exponent 2. Sorry, I said 2 to the exponent 2, didn't I? 2 to the exponent 1. Now, what's really important for us to understand is if I made my rate go up by a factor of 3, so if I tripled a concentration. And I did it again, I said the rate went up. If my concentration goes up by a factor of 3, I'm looking for the exponent on 3 for my rate. And once I know the exponent on, in this case 2, from the concentration that gives me my answer on the rate, I can fill that in on the rate law. All right, well there's that bit about K, the rate law constant. What do we do with that? More math. Now we're not going to do it all here, we're not going to work through it on here, but really what it comes down to is once I know that my rate is, I know the exponents, I have that, the only thing I'm really missing is that value of K. So if I look at trial number 1, I had the value of the rate, I had the value of concentration of each thing, and now I know the exponents. So the only unknown thing in that expression is K. So I would solve for K. However, we'll do that in class, and what we'll end up doing is paying more attention to the correct units on K, because that's where people are going to get stuck. Now I know this stuff seems kind of weird, and if it made a lot of sense, that is awesome. We'll do some examples in class. I'll give you some, hopefully lots of practice so you get this stuff nailed down. And again, please be aware that K is not just about coming up with the numbers, it's going to be about coming up with the units, and that's usually where people run into some trouble. So when we get there, pay particular attention to that. But we'll see you in class.